Hello guys, in this video I am going to solve this question number 10 of chapter 8 from this book Engineering Circuit Analysis by Hayt, Kemmerly and Dermot. So the question is that for this particular circuit it is given that the switch, this particular switch, it was open for a really long time. It means that when the switch is open, then the condition of the circuit, it will be something like this. Something like this branch, since the switch is open, so it remains open, so we can simply put it in this way. So in this situation, like 5 kilo ohm, it is 10 kilo ohm. This is our inductor, which is having the inductance of this, right? And this is 1.5 volt. Let me put this also, right? So over here you can see that since this branch it is open, so our current IW, it will be 0, right? Initial IW at t less than 0, it is 0 ampere. But what about current IL? Now since the battery is constant, and we know that the voltage across the inductor, it is given by L di by dt, and since the voltage is constant, it means the current through this circuit, when the circuit, like since the circuit is in this state for a very long time, so it means this constant IL, this current IL, it is constant, and since IL is constant, so this term becomes 0, and due to this term becomes 0, voltage across the inductor, it will be 0 volt, and since it is 0 volt, it means that there is no voltage drop across the inductor, and it means that inductor can be replaced with the short circuit. So we can simply remove this, right? We can remove this, and we can replace it with a short circuit. So now the current that is flowing through this, it is IL. Now for this particular arrangement, if I because we have simply 5 kilo ohm, 10 kilo ohm, so if we determine the IL, then IL, it will be expressed as 1.5 the voltage divided by total resistance, and remember it is kilo ohms. So the answer we will get is 1.5 upon 15 k, it means 0.01 milliamperes. So the current at t less than 0, it is 0.1 milliampere. So let me write it over here. IL at t less than 0, it is 0.1 milliampere, right? Now it is given that this switch is closed at t equals to 0. Closed means that the switch is now in this state. Let me use another pen. So the switch is now closed, and since now the switch is closed, so it means that the current that is coming through through this voltage source 1.5 volt, all this current will just move through this short circuit path, because current always follow the short circuit path, minimum resistance path. And similarly, now as no current is flowing through this branch, as no current is flowing through this particular branch, so inductor, because over here we have the inductor present, right? So inductor will try to maintain the current, means inductor will try to maintain this particular current, so inductor will come into picture. So over here this short circuit path will be removed. It will be like the inductor come into picture, and the current, inductor will try to maintain this IL current, right? And again the current through this, let it be ILT, right? So this current will flow through this path, and then again all this current will just go through this path, right? Because it is a short circuit path. And again, similar to this red color current, similar to the current because of this 1.5 volt, the current due to the inductor, it will also take the short circuit path, right? So because of this particular thing, because it is a short circuit path, so what we can do, we can like use the superposition theorem to solve this. Because over here this inductor presently it is acting as a source, right? How it become a source? Because when the circuit was open, for a very long time, this inductor has stored energy, and now that energy is used to maintain this current, right? So presently this inductor is acting as a source. So it means we can say that we have two sources. One source is this 1.5 volt and another source is the inductor. So we over here, since we need to, the question is that we need to obtain the expression for IW in the circuit, which is this. So what we can do, we can simply use the superposition theorem. So what is superposition theorem? With superposition theorem, we know that it says that if there are two sources, so we will activate one and we will deactivate the other, right? So if we, in the first case, if we keep this as active 1.5 volt, so the our circuit, it will be something like this, right? It is 1.5 volt, it is 5k, and now this circuit, it is 10k, and this inductor, it will be replaced with a short circuit. Why? Because this inductor, it is acting as a voltage source. So this will be replaced with a short circuit path. So since it is replaced with the short circuit path, so what we will get now, the current that is coming through this current, it will take the short circuit path, and since it is going to take the short circuit path, so no current flowing through this. Over here I will be 0. Since I is 0, so simply we can remove this part of the circuit. So overall we left with this part, right? So for this particular case, we can determine IW, let it be dash, IW dash. Now similar to this, in the second case, we will keep this inductor as active and we will deactivate the voltage source. So in this situation, like if I draw this, the circuit will be something like this, right? It is 5k, it is 10k, it is our inductor, which is 20 microhenry, right? And the current over here, it is IL, right? So over here, let this current, let it be IW double dash, right? Because I single dash I have already taken for this. So over here again, the current due to this, it is going to take a short circuit path. So this current will be 0, and since it sorry, so since it is 0, so it means we can remove this part of the circuit. So removing this part of the circuit, so we'll left with only this part, right? Now it means now we need to determine this IW dash and IW double dash. Now for this particular circuit, simply we have one voltage source and one resistor. So the current IW dash, it will be 1.5 divided by 5k, it will be 0.3 milliamperes, right? 0.3 milliamperes. Now similar to this, 0.3 milliamperes. Now similar to this, now for this circuit, if you look at this circuit, we can compare this circuit with a simple RL circuit, right? RL, and we know that for this circuit, this current IT, it is expressed as IT, it is expressed as I naught e power minus R by L T, right? So it means over here in our circuit, R is this, and L is this, right? So, and what is our I naught? I naught we have already determined. I naught is the current at t equals to 0, initial current, which is this. So our I naught will be, this will be our I naught, which is 0.1 milliampere, right? So it is 0.1 milliampere, so 10 power minus 3 to convert it into the ampere. E power minus R is 10k, so 10,000 divided by L. L is 20 microhenry, so 20 into 10 power minus 6 t, right? So simply we can get IT is equals to 0.1 into 10 power minus 3 e power. Now this and this is going to cancel out, right? So right, so we will get minus 0.5 into 10 power minus 9 t, so amperes. Or to convert it into milliamperes, we can remove this. So what we will get? We will get 0.1 e power minus 0.5 into 10 power minus 9 t. So this is our ILT, IT, this current. Let me write it as ILT, right? And the unit is milliamperes. Now over here, this is the same current that is flowing over here. Means if this current is ILT, then we can write that because the direction of this IW double dash and ILT, they are different. So IW double dash, it will be equals to minus of ILT, right? So it means that IW double dash, it will be 0.1 e power minus 0.5 into 10 power minus 9 t milliamperes, right? So now we have determined the current due to the inductor, which is IW double dash. We have determined the current due to this source 1.5, which is IW single dash, which is 0.3. So now we can simply write the total IW, the IW current that is flowing, IW current that is flowing through this short circuit path. It will be IW will be equals to IW single dash plus IW double dash. IW single dash, we got it as 0.3 milliamperes plus IW double dash, we get it as, sorry, minus. Over here we have minus, right? Because we get this expression. So it is minus 0.1. So minus 0.1 e power minus 0.5 into 10 power minus 9 t, right? 90, and it is milliampere. So in simple words, we can write IW, it is equals to 0.3 minus 0.1 e power minus 0.5 into 10 power minus 9 t milliamperes, right? Now this is the answer to the first part of the question, which says that we need to obtain an expression for IW in the circuit which is valid for t greater than equal to 0. So this is the answer to the first part of the question. Now what is the second part? The second part of the question, it says that we need to calculate IW at t equals to 0 and t equals to 1.3 nanoseconds. So B at t equals to 0, simply we substitute t equals to 0 over here. So substituting this value over here, we will get IW is equals to 0.3 minus 0.1 e power 0, right? Because t will be 0, so it will be complete 0. So 0 milliamperes. So this will be 0.3 minus 0.1 into 1. So 0.2 milliamperes. This is IW at t equals to 0. Now second part of the question, it says, like the second part of B, it is saying that what is the current IW at t equals to 1.3 nanoseconds. So at t equals to 1.3 nanoseconds, our IW, it will be 0.3 minus 0.1 e power, it is minus 0.5 into 10 power minus 9. So minus 0.5 into 10 power minus 9 t. Now the t is this. 1.3 means 1.3 into 10 power minus 9. Okay. Sorry, this expression, like over here it will be plus 9, not minus 9, it will be plus 9. You can see that over here also, like this expression, it is the expression that we obtained, like over here. Yes, over here we have this. So over here, if you solve this one, so it is 1000 divided by 2 into 10 power minus 6. So it is like in the numerator, it is this 0 is cancelled, so we have 1000, right? So it is minus 10 power 3 upon 2, and if we take this 10 power minus 6 in the numerator, so we get this. So it is minus 0.5 into 6, right? So it is plus 9, right? So plus 9, and now into t. So over here, substituting the value of t, which is this 1.3 into 10 power minus 9 seconds. So we are substituting this, we get this, and solving we get this, and this will be cancelled out, so it will be minus 0.65. so it will be 0.3 minus 0.05, so 0.25 milliamperes at t equals to 1.3 nanoseconds. So now if you apply the reasoning over here, what happened, that in this, let me clean this circuit little bit. Now over here, if you look at this circuit, we have determined that the current through this 1.5, it will be 0.3 milliamperes, right? And the current direction is from top to bottom, and the current through this inductor, it will be in this direction, right? This is ILT. Now we know that in the starting at t equals to 0, the current will be IL, current will be some finite value, but as t tends to infinity, this ILT, it is going to decay, means it is going to become 0 amperes, right? It means, and since over here the direction of these two currents, one because of 1.5, another current because of this inductor current, since the directions are opposite, so it means the inductor current is trying to reduce the IW current, means this 0.3, impact of this 0.3 will be reduced because of this ILT. So as in the starting, the value of ILT, it is 0.1 milliampere. So this 0.1 milliampere is going to reduce this current to 0.2, right? 0.3 minus 0.1, because current directions are in opposite direction. But as time increases and as at t equals to infinity, this ILT current becomes 0. And since it is 0, so there is nothing to, this current is not there. There is nothing to deduct. So this 0.3 current will remain as it is. So it means that this current, 0.3 current, in the starting, it will be 0.2. At t equals to 0, it will be 0.2. But as with time, this current is going to increase. Why it is going to increase? Because this IL current, it is going to decay. It is going to become 0 with as t tends to infinity. So as t tends to infinity, IW current is going to grow exponentially from 0.2 to 0.3. And this is what we can observe over here, that at t equals to 0, the current is 0.2, and at 1.3, current has increased. It has increased from 0.2 to 0.25, right? And if I substitute, like if in this expression, if I substitute t equals to infinity, then what I am going to get? I am going to get IW equals to 0.3 minus 0.1 e power minus infinity, because t will be infinity. So it will be upon e power infinity. This e power infinity, it will be 0.3 minus 0.1 upon infinity. So it is 0.3 minus 0. So 0.3 milliampere, right? So you can see that the logic, the theoretical concept, the theoretical concept that I just mentioned, it is just reflected by the derivation, by these values at t equals to 0, at t equals to 1.3, and at t equals to infinity. So with this, I end this video. If you have any doubt, you can put it in a comment box. Do subscribe my channel and share this video with your friends and colleagues. Thank you.